All right, so the example 5, okay, so we're doing 2.4, right? So operators, okay, of functions, right? So we got some functions, right? F plus g of x. What's the definition? This is f of x plus g of x, right? And then f minus g of x. This is f of x minus g of x. Third one, f times g, which is a product function. This is f of x times g of x, okay? And the last one, f over g, the quotient function. This is f of x divided by g of x, okay? So it's kind of straightforward, okay? So, but the last one is what? The composition, which is f after g, okay? The circle is the symbol of the composition, and then the definition of composition is f of g of x. Okay, so it means that we use the output of g as input of f. Okay, so remember that. So here is the domain. If we just express that composition as a diagram, we got this one. It's a domain of g. Okay, so here, and then here is the range of g. Right. Okay. So now the other one is this is the domain of f. Okay. And then this is a range of f. And then some part, that's the range of f after g. Okay. So what that means, you see that? The f after g means that starting from the domain of g, you see that? The domain of g, and then we're gonna get the definitely g of x, which is output of g, gonna be part of the range of g. But um, the out of the output of g of x, the what we have to take out the output, some outputs of g of x does not belong to the domain of f. It means that we have to find out the intersection of domain f and the range of g, which is this. So that's going to be what? The domain of composition f after g. Okay. And then now what? Then all the numbers in belong to domain of f after g goes to the here. Okay, because eventually what? We're gonna evaluate f, right? So the output of f must belong to what? Range of f. Okay. So keep in mind this right here. On this one right here. Okay. Oh, not domain of f. So this is, yeah, it's not domain of f, something like this. Should be here. Yeah, what I'm doing was a mistake. Give me a second. So right here, some part of that. Okay. From here to here. Okay, from here to here. All right, so that's going to be domain of f after g. Sorry. Okay. Then this one goes right here. Okay. So that's the diagram of composition of f and g. Okay. So, but let me, yeah, we may just say that it's a little bit abstract. So let me give a specific example. Yeah, that's the example 5. So it's the example 5 textbook. So f of x, that's the defined by the square root of x, so square root function, right? And then g of x defined by 2x minus 1, right? Okay, and then h of x, just a square function. Okay, so b, because I did a last time, so b, g after f of 5. Okay, so the specific number is what given instead of x, then you don't have to try to find out equation of decomposition. Okay, you just, yeah, using starting from definition of composition, which is g of f of 5. Now you evaluate the f of 5. Okay, so starting of what, 5, what, the f of 5 is what, square root of 5, right? So this is equal to g of square root of 5, right? Because what does that mean, f of 5? It means that y value corresponding to x value 5 under the function f. Okay, so it means that we plug in, I mean, technically just plug in 5 into x in the equation of f. Okay, the g of square root of 5 is what? That's the 2 times square root of 5 minus 1. Okay, okay, let's do a. I know, so we did a, but let me do it again. Okay, so f after g of 5, this is what, f of g of 5, right? Okay, so yeah, what's g of 5? So g of 5 is what? This is a 2 times, I mean, f of 2 times 5 minus 1, is it? Because I plug in 5 into the equation of g, which is 2 times 5 minus 1, which is 9, right? Okay, so this is f of 9. Oh, sorry, let me do it right here. This is f of 9. So f of 9 is what? The square root of 9, which is 3, right? Okay, so let me see, look at this. Let me express that process to get the 3 from the composition of f and g in that diagram. So starting from 5, definitely 5 is right there, right? Okay, 5 must be the what? The one of the number in the domain of g, right? And the 5, and the g of 5 is what? G of 5 is 9, right? So it goes to a 9 right here. Here's 9 right here. Okay, and then f of 9 is what? F of 9 is square root of 9, which is 3 right here. Okay, so okay, maybe a number which is right there. Okay, so that g of 5 is not uh g of 5. This is function g. Okay, this is function f. Sorry. Okay, this is function g. Okay, this is f. Okay, so definitely maybe there is a number which not belong to the domain of f after g. What I mean is, when you evaluate, when you find that y value corresponding to that number through the g, that one goes to that number right here, which does not belong to the intersection of the domain of f and the range of g. Okay, so that the f of that number does not exist, because that number is out of domain of f, so we cannot evaluate the f at that number, which means that this number should not be what belong to the domain of f after g, composition of f and g, right? So something like here is this, no, there's no, yeah, it can be. Okay, so now next one, let's see. Give me a second. Then c. Give me a second. Let's see, what's the c? All right. Oh yeah, f, the last problem, f after g after h. All right, so yeah, 3 functions are coupled with operator composition. How can you solve it? Yeah, we just apply the composition definition combination from the last to the first, okay, to the right to the left. So well, first we think about the composition of G and H, which is G of H of X, right? And now we think about the composition of F and composition of G and H. which means that we're going to think about composition of f and g of h of x, which is f of g of h of x. Okay. So now then this is equal to, yeah, so I think, yeah, I need, yeah, so next, let's see, we will find that f of g of h of x, right? So this is equal to, what is h of x? The square root of x, right? So we got h of g of square root of x. Okay, I just replaced the, what, h of x as the definition of the h, function h, which is the, oh, x squared, right? I'm sorry, this is x squared. X squared, sorry. So now that is equal to, this is equal to what? F of, and g of x squared is what? Since g is 2x minus 1, so replacing x by x squared, we're going to get 2 times x squared minus 1, okay? And then this is equal to, now, function f is square root of x. So the square root of 2x squared minus 1, that's going to be answer, right? Square root of 2x squared minus 1. Okay, so, but what's the domain of the, the function composition of f, g, and h? What's the domain? So then, yeah, it's kind of, yeah. So find out this one. Then we have to think about the what? The inequality 2x squared minus 1. I know the problem doesn't ask you to find the domain, but oh, state is domain. Yeah, so state is domain. Let's find the domain too. Sorry. So to figure out the domain, the what we need to solve that inequality. Okay, you got it. Why we have to solve that inequality? Because see that 2x squared minus 1 is the what quantity under the square root, right? So it means that 2x squared minus 1 must be greater than or equal to 0. Otherwise, we're going to get the imaginary number, right? So 2x squared minus 1, it must be greater than or equal to 0. So the what? 2x squared minus 1 is what? Actually, what? We're going to use, this is a quadratic. If you just think of this one as an equation of function, then this is actually a quadratic function. I know we didn't learn, we didn't learn the quadratic function yet, but we'll do that. But what the see, yeah. So, but we can solve this one using the what using the transformation. Remember that the solving inequality by reading the graph using transformation. We learned that in 2.3, right? So let me use this. So let's say what let me use the letter f, okay? F of x as a 2x squared minus 1, okay? Then let's plot the graph of f of x from the, starting from the graph of the just square function, x squared, parabola. And then we're gonna use transformation, okay? So let's say g of x is x squared. Then what? Using the, what? Stretching, okay? So by factor of 2, then we're gonna get the 2 times g of x, which is 2 times x squared, right? And then now we use the Fourier translate. We apply Fourier translation. I mean, shifting graph of 2 times g of x downward 1 unit. So we got 2 times g of x minus 1, which is 2x squared minus 1. Right? Okay, so this is exactly the same as the equation of f of x. And now what? Yeah, we plot the graph. So here's x-axis, here y-axis. Okay, so starting from the graph of the x squared, which is this graph of g of x, which is x squared. I know it's a little bit okay odd, but okay. Now we stretch graph of the g of x by factor of 2 to win get this, right? Okay, so we got this one. Okay, that's graph of what? 2 times g of x, and then we shift downward. Okay, so 1 unit. So we got this. Okay. So that's going to be 0, 0 goes down 1 unit. So this is going to be negative 0, negative 1, right? Okay. All right. So now what? As you can see that from the intersection right here, I mean, this is graph of what? F of x, right? So we need to figure out the x coordinate of those two intersection point, because from here to close, right? Close interval from here to here, in this interval, I'm sorry, so negative infinity to that close point, close interval, and then that close interval from that point to the infinity. On those two interval, what? The f of x gonna have positive number, right? Because we want to find out 2x squared minus 1 is greater than or equal to 0. It means that f of x is greater than or equal to 0, right? So, but f of x is nothing but y value. So we want to find out the interval on the x-axis where the y value is positive number, or or 0, okay? Greater than or equal to 0, I mean. So in this interval, since the graph lies above the x-axis, so that the well, it means that y value must be greater than or equal to 0, okay? So let's find out those two intersection points. How can I find out? Yeah, so we solve what? 2x squared minus 1 equals 0, right? And then what? X squared is what? Just 1/2, right? So x is what? Plus minus square root of 1/2. Okay. So this is equal to what? Plus minus 1 over square root 2, right? Okay. So it means that this is what? Negative 1 over square root 2. That is what? Positive 1 over square root 2. Okay. So the answer is what? Domain. Okay. So domain is what? Negative infinity to negative 1 over square root 2. Okay. And the union, positive 1 over square root 2 to infinity. This union right here. Okay. So now next one. Let's see. Yeah, let's see example 7 textbook. Okay. Give me a second. All right, so example 7. So f, g, h are given as equation, and write each given function as a composition of appropriate functions chosen from f, g, and h. All right, so yeah, the problem is really interesting because normally, the problem asks you to figure out composition of f and g, or g and f, or f and g and h, but this is a completely backward. The what? The result of composition is given. Okay, so you can see that what f, capital F, and g and h are obtained by composition of f, g, or h. Okay, so maybe f and g, or f and h, or we don't know. We need to figure out that. Okay, so it's completely opposite, right? So this is really interesting. So let's see. Now f, let's see. What f? This is example 7. So f of x, this is the square root of x, and the g of x, this is x minus 3, and the h of x, which is 2x, right? Okay, let's do a. Let me do a. So capital Fx, this is the square root of x minus 3. Okay. All right, so now to figure out how we can get, this one, capital F, the function, by using the composition of f, g, and h, then we have actually 6 possibilities, right? F, g, more than 6, f, g, and h, or f composition g, H composition at G, okay? So or F composition G, or just H composition G, something like this. So then do we have to do all of them? Yeah, it may take too long, so to figure out that, let me do the other way. So we just take a look at the type of the equation of F, okay? So it's the square root of x minus 3. It means that the square root function must be involved to get the square root, right? So you see that F, this function is the only function involved the square root. So the F must be involved. And then look at this, 2x, h of x, the function h of x, the coefficient of x is 2. But look at this, under the square root, the capital letter F, coefficient x is 1, not 2. So h cannot be, should not be involved. So in the x minus 3, so x minus 3 is exactly the same as the equation of g, right? So g must be involved. So we have two possibilities, f after g or g after f. Okay, so since this possibility is reduced by just only two possibilities, right? So let me do this. F after g is what? F of g of x, right? So this is g of x is x minus 3. So this is equal to f of x minus 3. Now, f of x minus 3 is what? That's the square root of x minus 3, right? So we got it. So this one is equal to what? F of f after g, okay? So we can get the square root of x minus 3 by doing just composition of f and g, okay? And then, yeah, similarly, we can do b and c, okay? So b, g of x is given as x minus 6, right? Then what? Okay, no square root involved. And then coefficient x is 1, not 2. So we drop the f and h, right? Okay, so, but the x minus 3 is not equal to x minus 6, right? Definitely different, right? So how can you get x minus 6 from the x minus 3? We do this. G after G. Okay, guys. Is it a little bit just, this is kind of tricky. But G composition G, then what do we when are we gonna get? We get G of x, which is what? G of x minus 3, which is what? X minus 3 minus 3, which is x minus 6. Okay, so now C. H, capital H is given by 2 times square root of x minus 3. Okay, then what? Definitely, the square root involved, so f must be involved, right? And then you see that 2. Coefficient of square root of x is 2, then h must be involved. And then minus 3, definitely this one comes from the g. So f, g, and h, all three functions must be involved in a composition. So then we'll do this. F composition, okay? And then g composition h. We start from this. But actually we have 6 possibility, right? So how many number of, how many possible, cases for combination of F, G, and H? 6, right? There are 6 cases. Do we have to do all of them? Now, first one, think about this. To get the two square root, we're just taking a look at this one as one single variable. Okay, one single variable minus 3. To get this one, then we have to get 2 times square root of x first, and then plug in, replace x by 2 times square root of x, right? So the h must be, g must be outmost the function in the composition, okay? And then what? And then to get the coefficient 2 and out of the square root of x, then what? We have to plug in, replace the x by square root of x. It means that, give me a second. F must be the outer function of the composition of the h, so this. Okay, or if you just confuse how we got this, think about this. F of h of x and the h of f of x. Think about this. F of h of x is what? F of h of x is the square root of what? The 2 times x, right? Oh, sorry, this should be h. This should be f. typo. So h of f is what? This is just 2 times square root of x. Okay. So we see that? That's what we want, right? Now h of f is nothing but what? H after f. Okay, that's what we got this. All right. And then what? The g of 2 times square root of x, this is gonna be what? 2 times square root of x minus 3. This is exactly what we wanna get, right? So g of 2 times square root of x, this is nothing but what? G after h after f of x, right? Okay, see that? So the answer is what? This is a g after h after f. Okay. So the similar problem to this in the online homework. So let's see one more problem similar to this one, and then we move to the 2.5. Okay. So give me a second. 2.4. Oh yeah. So 2.4. Let's see. No. Yeah, you see that? So FGH, let f of x is the square root of x, and the g of x defined by x minus 4, and the h of x defined by x squared. So write f of x, I mean capital letter f function, x squared minus 4, excuse me, as a composition of functions. So which of the following compositions correctly defined? So let's see. All right, so what I do, yeah, so let me clean up. All right, so okay, let me copy the functions. So this is problem number 6, okay? And then f of x, divided by absolute of x, the g of x, x minus 4, and the h of x, x squared, okay? All right, so f of x is x squared minus 4. All right, so the regenerating function, okay, capital letter F, x squared minus 4. So see, x squared is involved, right? So the h must be involved, which is square function, right? Give me a second. All right, and then minus 4, yeah, so g must be involved. Okay, and I don't see absolute value, right? So f, I don't think f is involved. Okay, so now then what? Now we gonna do what? We try to evaluate composition of g and h, or h and g, right? X, okay. So this is a g of h of x, which is what? G of x squared. That's gonna be x squared minus 4. Okay. So that is h of g of x, which is what? H of x minus 4. That's gonna be what? X minus 4 squared, right? Okay. So yeah, definitely x squared minus 4. That's the answer, right? Okay. So g after h. Okay. So that's gonna be answer. Okay. So that's for the 2.4. Now we move to 2.5. Okay. So in 2.5, the objective, yeah, 2.5, we're gonna learn the inverse function. Okay. So objective, yeah, definitely we need to learn the definition of inverse function, right? Definition of inverse function. Okay. Yeah, simply saying that what's the inverse function? Inverse function is we can get inverse function by interchange domain and range. It's really simple, right? Okay. But think about this. Um, I mean, okay, so then here's a question then. Can you get the I mean, once we interchange in domain range, then is that gonna satisfy definition function? That's a different story, okay? So yeah, simply just interchange domain range of a certain given function. Okay, this is not a big deal. Okay, so just interchange the x coordinate, y coordinate for every single d order pair, the set of function, right? Or in yeah, simply saying that. But once you interchange first coordinate, second coordinate, then is you know is you know is that the set gonna be a function? That's a different story. Maybe yes or no. Okay. So we're gonna think about this. So the what in order to that, once you interchange and domain range, and still we get a function. I mean, the function obtained by interchange domain range is still function. In order to that original function must be one-to-one. So we need to learn the one-to-one function. So this is the actually necessary condition in order to exist the inverse function. Okay. Oh, not one-to-one function. So now third one, yeah, once we figure out definition of inverse function and the one-to-one function, but actually we need to I'm gonna cover one-to-one function first because this is really important, and then we see definition of inverse function, and then we see notation of inverse function, and then specifically we need to figure out how to find inverse function, right? Okay, so okay, so that depends on strategy, depends on the how you know what function is given. Okay, if the problem is function given by set ordered pair. Okay, okay, then we simply just switch in. Definitely, the very first step is to check whether or not given set ordered pair satisfy definition of one-to-one function. Okay, if yes, then we just simply interchange domain range. I mean, first coordinate, x coordinate for each of the order pair. Okay. So what if we just the problems give you the function as a graph? Okay. Given the graph, then we apply the horizontal line test. In this case, we apply yeah the horizontal line test. Okay. So the last one is what if we just function is given by the equation? I mean, okay, algebra expression. I mean, okay, is an equation. Then we use the switch and solve method. Okay. So I'm gonna cover this one next time. Okay. So I'll cover up to here. Okay. So yeah, and then we're gonna see the relationship between the graph of function f and the graph of function inverse graph of inverse function of f. Okay, we need this. So, but anyway, I'll cover up to here. Okay, so think about this. Let's see, one-to-one functions. Give me a second. Yeah, so let's see, one-to-one functions. So here's the definition of one-to-one function. If a function has no two ordered pairs with different first coordinate and the same second coordinate, then the function is called one-to-one. This is really similar to the definition of function. That's why I told you when I introduced definition of function, you need to remember this one carefully. You're gonna see really similar one later. That's it. That's the one-to-one function. So definition of function is what? The no two pairs with the same first but different second. But in one-to-one function, different first, same second. Okay, keep in mind this. So, okay, so yeah, but what's the meaning of one-to-one function? So, yeah, let me explain about this. Okay, so think about the function x squared. So we know the graph of x squared, which is parabola, right? So this is the graph of f of x, which is x squared. Okay, so think about this. Here's 2. Let's figure out the ordered pair whose x coordinate 2 and negative 2. Okay, so then when x is 2, we're going to get 4, right? 4. Then here's a 4 right there, right? So this is 2, 4, and then this is a negative 2, 4, isn't it? Okay. So now, what's the domain? Domain is what? Negative infinity, infinity, right? This is domain. And then the range is what? 0 to infinity, right? This is range. So domain is negative infinity to infinity. The range is what? Closing number 0 to infinity, right? Okay. So I told you what's the inverse function? Inverse function is just we can get inverse function by interchange and domain range. Okay, let's interchange domain range. Okay, it means that we interchange what? X coordinate and Y coordinate. So we're gonna interchange X coordinate and Y coordinate of those 2 points too. Okay, then we're gonna get what? 4, 2 and then 4, negative 2, right? Here's 4, 2 and 4, negative 2. Okay, but see, actually, graph of the one graph of the function, I mean, not function, graph, you know, I mean, when we just interchange an x and x coordinate, y coordinate, not just 2 points, but every single point, the graph of f, we're gonna get this. Okay, we know that this doesn't satisfy what the definition of function. Why? Because when you look at this intuitively, this graph doesn't satisfy what vertical line test. The vertical line test is one of the methods to check whether or not given graph is a graph of function, right? So this vertical line meet the graph more than once, so it means that this is not a graph of function. Okay, so it means that what? This x squared does not have inverse, does not have inverse function. It means the inverse function, excuse me, inverse function of this one does not exist. But anyway, so but let me just take a look at 2 points. 4, 2, and then 4, negative 2. Or we can, I mean, without, the applying the vertical line test, we can say that, you know, the interchanging, the graph obtained by interchange domain range of f cannot be a function because see that these two ordered pair have the same first but different second. This is the what? The violation of definition of function, right? Okay. But what if these two guys have the you see that? Excuse me. So how we got 4, 2 and 4, negative 2? Because of 2, 4 and negative 2, 4. See? So right there, give me a second. Give me a second. All right, so we got 4,2 and 4,-2 from the those 2 points, right? 2,4, -2,4. So what if these two guys have the I mean, just look at this. These two guys have different first but same second, right? You see that? 2,4 and -2,4. These two order pair have the different first, same second. That's what we got those 2 points, which is the what? Which is the on the same vertical line, right? Pass through the same vertical line. So that's why in order to have the inverse function of the function f, then no such a pair is an ordered pair, which means that a different first, same second. And then the let's see 2,4 right there. Let me say this is 2. I mean -2 and yes, so 2 and -2. Okay, so here's f and then 4 right there. So 2 goes here, -2 goes right there. Okay, so now then what? The key mind is this one satisfies the, I mean, the definition function, right? So do not be confused. Definition function is what? For every single, I mean, other definition of f, then other definition function is this. For every single number on the domain has a unique y value. Yeah, so even though these two x values share the same y value, but individually, each x value has unique y value, right? Okay, so only one, the corresponding only one y value. That's what I'm saying. So this is a function, but this is not one-to-one. Why? Because two distinct x value correspond to the same y value. Okay, so that's the meaning of one-to-one function. So this one is a function. F is a function, but not a one-to-one function. Okay, then what about this? This is a domain range right there. What about we got this? Then this is not a function. That region is not a function. Okay, mind this. Okay, so now then if we got this one, then this is one-to-one. This is a function and a this is on right on one-to-one function. Okay, one-to-one function. Okay, mind this. So now you see example of example 1 that in the slide. So determine whether each function is one-to-one. So so what are you gonna do? We've tried to find that two order pair have the what? The same second but different first. So but see all order pair have what? Distinct y value and second coordinate. So 3, 5, 4, 9, 0. So yeah, definitely this is one-to-one function. And then B, you see that 4,16, -4,16. These two guys have the same second but different first. So then this is not one-to-one function. So that this set doesn't have inverse function. It means that when you interchange x coordinate and y coordinate, that's not going to be a function. Okay, the set obtained by interchange x coordinate and y coordinate, the set will not be a function, cannot be satisfied function. Okay, C 3,0.99 and then 9,0.99. You see that these two order pair, first order pair and the last order pair, had the same second but different first. So C is not a one-to-one function. Okay. So now horizontal line test. I told you. Horizontal line test is what? Similar to vertical line test. We use this one to to figure out whether or not given graph is graph of one-to-one function. Okay. So we drew the horizontal line. If that line meet the graph more than once, then the line is not a one-to-one function. Okay, I told you it's not. I'm saying that what I'm not saying that it's not a function. Maybe it's a function, but not a one-to-one function. So one-to-one function is what the more a stronger condition than the function. What I mean is this is the set of the function. Okay, the set of function. Right then, 1 second. See. Mm, okay, that's good. So here this is the set of functions right here, and then the set of one-to-one function is inside of set of function. Okay, the set of one-to-one function. Okay, so that means one-to-one. Okay, okay. So what about the right here? This is certain function belong to right this one. That means that these are functions, but not one-to-one. But right here, a function belong to this circle. This set means that this one must be function. I mean one-to-one function as well as function. Okay, so one-to-one function is special case of the function. Keep in mind this. So now, yeah. See example 2 in page 227. Okay, so give me a second. Let's see. Yep. So yeah, give me a second. Oh. All right. So see the example 2. So use the horizontal line test to determine whether the function is shown in figure 2.57. See, this is a graph of the absolute function. So this is one-to-one function? No, because you see that horizontal line meet the graph twice, right? Then cubic function, yes, cubic function is a one-to-one function. So because see, as you can see that horizontal line meet the graph once. Okay. So now next one, there. So next one, inverse function. Yeah, so now we see a definition inverse function actually. So if the original function is one-to-one, then the set obtained by interchange the coordinates in each order pair is a function, the inverse function. That is called inverse function. So if a function is one-to-one, then it has an inverse function or is invertible. So keep in mind it's invertible. Invertible means that terminology means function is one-to-one. So that the function has inverse function. Okay, so let's see example 4. For each function, determine whether it is invertible. If it is invertible, then find the inverse function. So yeah, so what? The f is what? Is inverse function. So you see that f and g, the functions are given by the set of a pair. Then we just directly apply the definition of one-to-one function to check that f is those functions are invertible. Okay. So I don't think f is invertible because first and last, see, the first and the last order pair has different what? The first is the same second, right? So the f is not invertible. Okay. What about g? G is invertible? Yes, g is invertible. Okay. Then what? What's the inverse function? Just interchange the first coordinate, second coordinate. Okay. So 3, 1 becomes 1, 3, 5, 2 becomes 2, 5, and 7, 4 becomes 4, 7, and then 9, 8 to 8, 9. Okay, that's gonna be the inverse function. But what's the notation? We use this. You see that right there in the exponent position, we put the -1. That doesn't mean that to the degree, okay? No. So -1 means inverse function. Okay. So inverse of one-to-one function is f is of f to the f inverse. Okay. So now, second. So now we'll see. Let's see example 5. So stop share. Okay. So example 5. This is example 5 in textbook. Excuse me. So f is given by set of 1, 3 and 2, 4 and 5, 7. Okay. And f inverse is going to be, by the way, is that one-to-one function? Yes, this is a one-to-one function. Okay. So why? Because see that all of the second coordinates are different, right? So the f inverse is going to be 3, 1, 4, 2, and then 7, 5. Okay. So that's f inverse. What's the f inverse of 3? That we find out second coordinate corresponding to first coordinate 3 in the function f inverse. You see that 3, 1, just 1 must be the answer. By the way, f inverse is really the function. Yes, you see that all of the first coordinates are different, right? Okay. So now, give me a second. So now, I mean, if you're really confused about the definition of one-to-one definition of functions, then just keep in mind this right here. If you got this kind of order pair, I mean, two order pair having relation like this, then what? Not a function. Okay. If you got this one, okay, not one-to-one. I told you, but let me tell you again. Okay. So just memorize those two images. Okay. So not one function y, because these two order pair has this have the same first, right? Why this is not one-to-one? Because these two order pair have the same second. Okay. So in the next one, what about the f inverse composition? F after f of 1. This is a really easy problem. This answer is 1. How come? Because f of 1 is what? This is the f of 1 is what? 3, right? F of 1 is 3. And the f inverse of 3 is what? 1. It's kind of back and forth, right? The back and forth. So this is always true. When you do composition of f and f inverse of any number, the answer is what? Same as the input. So f inverse composition of f of x, this is equal to x. Even though you switch f and f inverse, you're going to get same result, which is x. So just keep in mind this, okay? So if you got this kind of problems, it's really easy. The answer is well, always x. Always, I mean input, okay? So now, let me see. Oh, yeah, we're gonna see the relationship between the two graph of function f and f inverse. So the conclusion is this. Let's see. Yeah, see, okay. So if, just look at this. If a point a comma b is on the graph of invertible function f, then b comma a is on the graph of f inverse. It makes sense. And then a comma b comma a is actually symmetric with respect to the line y equals x. It means that two lines, the graph of f and the graph of f inverse, must be a reflection about the y equals x, line y equals x. Okay, so let me give you an example. So now, okay, so hang there. So I'll cover this one and then just call it a day. Okay, so now the what? F, think about this. The x squared, f of x is equal to x squared. So I know Um, well, it turns out that this function doesn't have inverse function because this is not one-to-one. I know, so, but we can make this one to be what one-to-one function. How come? We just restrict the domain from 0 to infinity, okay? So we only consider the, what, this function, this side, okay? All right, all right. So now, here's the domain, okay? We restrict the domain to from the negative infinity to infinity to just 0 to infinity. And the range is same, okay? 0 to infinity, okay? Then this function is gonna be one-to-one function. Why? Just draw the horizontal line. The horizontal line beta just grab once, right? Then the inverse function is actually this. I mean, think about this. The Give me a second. Function must be actually give me a second. Yeah, it's like this. Okay, because see the look at this. This is graph of y equals x. So we just reflect the graph of x squared about the line y equals x. Then we're gonna get this like this. So two graphs reflection about the line y equals x. So this is f inverse. Actually, graph of equation of f inverse of x squared is what? Actually, square root of x. Actually, okay. We're gonna figure out why the yeah. So why the equation of f inverse of the f is square root of x next time. Okay. So from here we can see that as long as you know the graph of f, you can plot the graph of f inverse by reflecting the graph of f about the line y equals x. That's the key point. Okay, so let me stop here, and then next time I'll finish the 2.5. Okay.